Good afternoon to all of you. So today, Dr. Zhong Han, who has recently completed his PhD, will be delivering a presentation which will be recorded and will be submitted to the Canadian Geotechnical Society graduate student competitions. So he'll be doing a 12 to 13 minutes presentation, followed with a couple of questions from the professors, graduate students, and undergraduate students. I thank you very much for all of you coming to hear this presentation.
Thank you.
Zhong Han, go ahead.
Thank you, Dr. Uottawa. Good afternoon, ladies and gentlemen. My name is Zhong Han from the University of Ottawa. Today, my presentation focuses on the modeling, stiffness, and shear strengths of unsaturated soils. The design and analysis of geotechnical structures actually need a lot more parameters. For example, a pit excavation in downtown Toronto actually will require very strict displacement control such that the surrounding building will remain safe. And in such case, we need stiffness and shear strengths within a very small strain. And for example, we need the small strain shear modulus in this case. For more regular geotechnical infrastructure, for example, those buildings, the pavements in Montreal, or the slope analysis here in our Parliament Hill in Ottawa. In those situations, we need the stiffness and shear strength parameters within the intermediate strain, which involve the elastic modulus, the peak shear strengths for the building and slope, as well as the resilient modulus, actually, which is needed in pavement design. In some cases where the large strain is encountered, for example, the tunneling project of LRT project here in Ottawa, or for some of the laboratory tests where we have this Champlain sea clay specimen being sheared to failure. And in those scenarios, we need the residual shear strengths or elastic modulus at very large strain levels. On the other hand, our geotechnical infrastructure usually stay beyond the groundwater table where soil stays in an unsaturated condition. And we should apply unsaturated soil mechanics instead of the traditional saturated soil mechanics. Predicting the shear strengths and stiffness properties for unsaturated soils has never been an easy job, and there are many different ways. For example, in the literature currently, at least 46 different equations are available for the shear strengths, 7 for elastic modulus, 15 at least for small strain shear modulus, and as per my statistics, there were 30 equations for the resilient modulus. So here is the question: will there be a uniform model that we can use to predict the variation of unsaturated soil properties with suction or with moisture content? And the answer is yes, we do. But before that, we need a very powerful tool, which is called the Soil Water Characteristic Curve, or SWCC. And SWCC actually describes the relationship between the moisture content within the soil and the suction. The suction actually is a free energy within the soil, which pulls the soil particles together such that it increases the stiffness and shear strength of the soil. For example, with the increase in the suction, there will be an increase, first linearly and then non-linearly, in the stiffness and shear strength of the unsaturated soil. Let's take the sandcastle example in this case. When the sandcastle comes with suction, the sand will have a higher stiffness and shear strength, and in this case, the sand is very easy to handle, and we can build a beautiful sandcastle like this. But if the water comes and the sand becomes saturated, the sandcastle lost its suction. In this case, we'll have a much lower stiffness and shear strength, and then the sandcastle will start to collapse. So The SWCC actually can be used as a very powerful tool, but how can we use it? We need two steps. The first step is transformation. For example, we have a SWCC which describes the relationship between the degree of saturation and the soil suction. But if we can transform this relationship into another form, we need a transformer. And then after transformation, the SWCC becomes like this. It's suction multiplied by the exponential degree of saturation versus suction relationship. And the exponent is called psi. In this case, the SWCC actually transforms to a shape like this, which is linear at the very beginning and becomes nonlinear with the increasing soil suction level. Let's recall the variation of the soil properties with suction. It is also linear and nonlinear characteristic curves. So in this case, there is a possibility that we use the similarity between this curve and this curve for prediction. But how can we use such similarity? We need the second step, which actually I call it normalization. Let's bring those two curves back. Linear to nonlinear, linear to nonlinear. If we can choose 2 points, with one point being the saturated value and the other point being a reference value, if we use the following formula by subtract the value from those two curves, by subtract the value from the values on those two curves by the saturated value, and then divided by the difference between the reference value and saturated value. Such formula for the SWCC will give us an equation like this. And then for the stiffness and shear strength will give us an equation like this. For example, shear strength, elastic modulus, small strain shear modulus, and resilient modulus. After the normalization, those two curves are normalized to the same scale, typically between 0 and 1. And if we can find a suitable fitting parameter, which is psi, that those two curves can be merged magically together, become 1. And in this case, if this is possible, we will obtain an equation like this, And then we can predict the variation of the stiffness, either it's tau, E, G0, or MR, with respect to either soil suction or degree of saturation or other moisture contents. In order to use this equation, actually, we need 4 pieces of information. The first being the SWCC actually can be conveniently measured in our lab. The second piece of information is a saturated shear strength and stiffness, which actually can be derived from the conventional soil mechanics. The third piece of information is the reference shear strength stiffness at just one point, which we can measure. And the fourth piece of information is the one parameter psi. We found that it's very encouraging that a psi value of 1 acts good for the cohesionless soils, and a psi value of 2 actually works pretty well with cohesive soils. In order to validate this equation, we actually have chosen 44 different soils from various continents in our world, and those data includes the testing data on the resilient modulus, shear strength, elastic modulus, and small strain shear modulus. And those data, it covers 12 different coarse-grained or cohesionless soils, as well as 32 fine-grained or cohesive soils. I'm just showing several examples of the prediction. The first example is on the elastic modulus of 4 different cohesive soils from Colorado, USA. Those are the SWCCs of those 4 different soils, and this is the prediction. As you can see, the dots with different colors represent the measurement, while the line with the same color represents the prediction. A very good prediction has been achieved for 4 of those soils. The second example is on the critical shear strength of two soils from Australia. And the hysteresis characteristics curves of the SWCC is highlighted here. And this is the SWCC for the two soils. And this is the prediction for the first soil, Berkey silt, as you can see the prediction. And then the second one is for the sand colony mixture. Also, the prediction is favorable. In addition to that, coming back to our equation, if we can express the saturated value, such as G0 sat or MR sat, as well as the reference values, such as G0 ref or MR ref, we express those parameters using a stress-dependent model. For example, for the small strain shear modulus, we can use this stress-dependent model. In this case, we can introduce the influence of the stress state into the prediction, and then we can predict a very smooth surface in the G0 stress and suction space. And this is a very smooth curve that also describes well the variation of G0 with both stress state as well as the suction. And here is another case for the resilient modulus. If the resilient modulus is expressed using another stress-dependent model. And then again, another smooth surface can be created and predict well the behavior of the resilient modulus. In addition, we also applied this model in Ontario. Recently, there is a cooperation between the Ministry of Transportation of Ontario and University of Ottawa working on a project to facilitate the implementation of the mechanistic empirical pavement design guide in Ontario. Here, we actually selected six different soils from different locations in southern Ontario. We use the GDS ELDYN testing system to test those 6 different soils. We obtained the resilient modulus as well as the shear strength and elastic modulus for all of those 6 different soils, as well as their variation with the soil suction and the moisture content. And this model has already been applied to all the testing data with favorable prediction results. I'm going to show 3 examples. This is the prediction result for a silty clay collected from Toronto. As you can see, this is elastic modulus, shear strength, and the resilient modulus. All predictions are favorable. And here's another case for a lean clay from Concardian, also in Ontario. Again, favorable predictions are achieved. And the third one is a little clay from Ottawa here, which actually is a marine clay which is sensitive in nature. And we can see good predictions also are available for this soil. So throughout this project, we have determined the basic soil properties, the optimal moisture content, which are the basic soil information needed in a pavement design. We also measured the California bearing ratio as well as the representative resilient modulus for all the soils as the design value for the pavement design in Ontario. We also investigated the variation of CBR and resilient modulus with suction and moisture content using our model. So at last, to sum up, in this presentation, we explored the possibility of extending the similarity between SWCC and shear strength or stiffness for prediction, and it worked. And then we came with a model which takes a form like this. In order to validate the model, we used 44 different soils from all over the world, and good predictions have been achieved. And in order to apply this model in Ontario to facilitate the better design of pavements here in Ontario, specifically, we use this model to predict the variation of resilient modulus with moisture content, such that the design of pavement in Ontario could take into account the influence of the environmental changes. And those are the references related to this presentation, and I thank you for your patience for this presentation. And I'm willing to take several questions. Thank you.
Thank you, Han. Questions? Dr. Infante Sedano.
Yes, thank you for your presentation. You mentioned in the equations that you presented, you always normalize and you need a reference value other
Yes.
than the saturated property, correct?
Yes.
What is, or do you have a recommendation as to what reference value one should choose, or does it make a difference?
Okay, thank you very much. Actually, the reference value is a key information needed to use this equation. For the reference value, most of the time for the engineered soil, we try to compact the soil, the natural soil, at its optimal moisture content conditions such that we'll obtain the highest shear strength or stiffness and the highest density. In this case, the stiffness and shear strength at optimal moisture content could be suitably used as the reference point. And this is also the case when we predict the resilient modulus for the different Ontario subgrade soils, because for subgrade soils particularly, we compact the soils exactly at its optimal moisture content as per the specification of pavement design guides.
Questions from students? Matthew? Yes, Jason.
Yeah, thank you, Dr. Han. I will continue with Dr. Infante's question about the reference point. Can we go back to page 4?
Okay. Go back to page 4. Yeah.
Yes, a little more. Yeah, it's okay. I have a question about the denominator as reference point minus the saturated point, right?
Yeah.
Do you think the choice of the reference point will have a large influence on the prediction results? Because if you choose the reference point larger, then you will cover more points between the separated point and the reference point. So what, that is my question.
Okay, actually, I agree with you for sure. The choice of the reference point will definitely influence the results of the prediction, because for the actually measured data, they will not strictly distributed along a very smooth curve. There should be some scatterness happening. So if you choose one point, then you will get a one curve. You choose another point, you will get another curve. But as has been shown in one of our recent publications regarding this model, when your measurements are reliable, actually the differences introduced by choosing different reference points is not significant and sometimes can be neglected. So for sure there will be influence, but if data are reliable, the influence or the differences between different predictions introduced by different reference values will be neglected.